In the previous two videos, we talked about electricity and we talked about circuits. And in this video, we're moving on to the second half of electricity and magnetism. So let's get started. Some types of metals can be magnetized, which means they have a north pole and a south pole. Opposites attract, and similar poles repel. And just like the electric field, we can have a magnetic field, which tells us what would happen if we put a north pole there. Now here's the thing. Moving charges also create magnetic fields. That's how the Earth's magnetic field works. And you can figure out how strong the magnetic field is going to be and what direction it's going to point in with the Biot-Savart Law. So let's break it down. dB is a small slice of the magnetic field. The fraction out front is just a constant, so we're going to go ahead and ignore it for now. The cross symbol represents a cross product between dl and r, and its magnitude is the magnitude of each of the vectors times the sine of the angle between them. But the direction can be found with the right hand rule. Take your right hand, point it forward, point your thumb up, and point your middle finger to the left. Now you have a right hand rule. If A cross B equals C, then your pointer finger is in the direction of A, your middle finger is in the direction of B, and your thumb is the output, the direction of C. Back to the Biot-Savart Law, this means if you point your index finger in the direction of the wire, specifically the direction that positive charges go, and your middle finger in the direction from the wire to the observation point, then your thumb points in the direction in the magnetic field. And at this point, I feel like it's worth mentioning that conventionally, current goes in the direction of positive charges. So anytime you see something about current and its direction, you always assume that it's going to be the positive charges that are moving, or in the opposite direction of the electrons. And anytime you see dl along a wire, it's going to be following the current. Lastly, the magnetic field is proportional to the current. So, more current, more magnetic field, and inversely proportional to r squared. So the further out you get, the weaker the magnetic field. Because of this law, the magnetic field is always going to curl around the wire of current like this. So another right hand rule you can do is make a thumbs up like this. Point your thumb in the direction of the current, and your other fingers will curl in the direction of the magnetic field. Or, if you want to, you can point your thumb in the direction of the magnetic field, and your fingers will tell you the direction of the current. This means that if you want to create a fairly consistent magnetic field, you can make a loop of current, like this. Putting it all together, to get the magnetic field of some running current, you add up the current times a small bit of length crossed with the radius, divided by the radius squared. In other words, moving charges create curling magnetic fields. Now here's the weird thing. Magnetic fields also move charges. Specifically, the force on a charge from a magnetic field is equal to QV cross B. This means that if a particle isn't moving, or has no velocity, then there's no magnetic force. Or, if the particle is moving parallel to the magnetic field, there's also no force. But once the particle starts moving slightly perpendicular to the magnetic field, then the charge experiences a force that's perpendicular to both its velocity and the magnetic field, specifically with the cross product. Now in this segment, we're going to be working a lot with three-dimensional vectors, which we usually represent as arrows. At the front of the arrow is a pointed tip, and at the back of the arrow is what's called feathering. So when an arrow points out of the screen, we draw a circle and a dot like this. And then when an arrow points into the screen, we'll use a circle with an X, which represents the feathering. So here's a question. If I have an electron going out of the screen and a magnetic field pointing to the right, in what direction is the force going to be in? Now has your chance to figure it out. Okay, time's up. Since the force equals QV cross B, we can point our index finger in the direction of velocity out of the page and our middle finger to the right, and this means that V cross B points upwards. But remember that electrons have negative charge, so the upward pointing force gets inverted and the electron actually experiences a downward force. Now that we know what forces act on a charge in a magnetic field, the next logical thing to do might be tracing out its path. So, let's assume we have a magnetic field pointing into the screen, and we'll send a positive charge upward to the right of it. Using the force equation and the right-hand rule, we can see that the force is to the left. So the charge will get pushed to the left until its trajectory looks like this. Now, its velocity is to the left. So if we do the right-hand rule again, we get that the force is downward, which pushes the charge downward, until it's going down and to the left like this. Now the force is to the right, so it goes like this, and then the force is up. So we can see that the charge follows a circular path. It's important to note that the magnetic field the charge creates won't push the charge itself, otherwise you'd have some kind of weird feedback loop thing. On each side of the charge, there's an equal and opposite magnetic field, which means that the force is going to cancel in all directions. If you have some general velocity and a straight magnetic field like this, you can break it into the components of the velocity, parallel and perpendicular to the magnetic field. The parallel component won't create any force, so the charge will just keep going in that direction. The perpendicular component will curl the charge in a circular shape, so when you combine them, most charges will follow a helical path when going through a magnetic field. This is how the northern lights work. Charges in the atmosphere get curled into a helical path because of the Earth's magnetic field, and for reasons we'll see in Chapter 4, these accelerating charges create light waves. Now of course this is only for a single charge. If you have a wire of charges, then you'll have to take the charge inside the wire. We've seen before that we can rewrite it with this geometric definition. So the charge inside the wire is equal to the charge carrier density times the charge on each carrier times the volume, or area times length. And if we let the length vector point in the same direction as the velocity, then we can swap them since the magnitude and direction are both preserved. And now the constants on the outside are just the current, because we go from length to velocity by dividing by the change in time, which is also how you get from charge to current. And if the magnetic field changes across the wire, then we can just add up the force across tiny lengths of the wire like this. So we get that the magnetic force acting on a wire of current equals adding up the current times a small bit of length crossed with the magnetic field across the whole wire. So here's a problem. I have a device that can measure the voltage just fine, but I don't have anything that can measure the magnetic field. Well, what I can do is I can position the magnetic field perpendicular to the current like this. Now the positive charges are pushed upwards, and as more positive charges start to accumulate at the top, they create an electric field, which opposes the magnetic field force until they're equal. So once they're equal, we know that the magnetic field force is equal and opposite to the force from the electric field. So Q times E should equal QV cross B. And since the current and the magnetic field are perpendicular, this simplifies to just QVB. Now we can cancel the Q's on both sides, and remember that the voltage is the accumulation of the electric field. We'll assume that the electric field is constant, in which case we get the voltage equal to the electric field times this distance, or that the electric field is the voltage divided by the distance. Substituting this in, we can solve for the magnetic field in terms of the voltage. We can calculate the velocity just like we did earlier, somewhere around 0.2 millimeters per second. Another example is two parallel wires like this. The bottom wire creates a curling magnetic field, which points out of the screen near the top wire above it. So our IDL cross B points downwards, which means that the top wire is getting pushed downwards. Likewise, the top wire creates a magnetic field that points into the screen near the bottom wire. So IDL cross B points upwards. The bottom wire is pushed upwards. So we can see that parallel currents attract each other. As a third example, let's look at a charged up capacitor, and we'll add some long wires extending from them to the left like this. Now, we'll add a magnetic field pointing out of the screen with something like maybe a permanent magnet in between the two wires. Lastly, we'll connect the circuit with a piece of wire that can move. So really anything that's conductive and metal will work. With a small resistance, we know it'll draw a lot of current. So this large current, I, times dl cross B, will then act as a large force to the left. And what we'll get is that the metal piece gets very quickly accelerated to the left. For one last example, let's put a loop of current inside a magnetic field, like this. We want to compute the torque on the loop, which is the same as the radius crossed with the force. If you push from further away or with more force, then you get more torque, which is going to want to spin the loop. Specifically, we'll want to get the torque that makes the loop spin on its top axis. So the force from the top and bottom wires both act vertically. Since those are parallel to our vertical axis, they're not going to create any torque around that axis. We can now limit our focus to just these two vertical wires. Let's take a look at the top-down view. We'll rewrite the cross product as r times f times the sine of the angle between them. Now, we know that the radius is just half the width of this top wire. So, we can rewrite it as w over 2 f sine theta. And there's two of them since we have two forces from each wire. So, when we combine them, we get wf sine theta. Now, the force we've seen before is IL cross B. And since our magnetic field, which points to the right, and our current length, which points out of or into the screen, are perpendicular, then F just becomes ILB. Now notice that width, or W, times L is the same as the area of our loop. So we can rewrite it like this. Now lastly, we'll define a vector called mu, which has magnitude I times A times N, which represents the number of loops if we were to have a multiple loop coil. The cross product of mu and B is the torque on our loop. This holds for any loop of current, and it's how motors work.
Now earlier, right after we talked about electric field, we did flux, and then we did Gauss's law. And you can do the same thing here, but the result isn't really that interesting.
Magnets always have a north pole and a south pole. If you cut one of them in half, you just get another north and another south pole. So any region of space is going to have a magnetic field flowing away from a north pole and towards a south pole. In other words, there's always going to be flow into and out of some region, and the exact amount makes it so that the flux always cancels. The magnetic flux of any closed surface is zero. A more useful thing for calculating the magnetic field is the magnetic circulation. Instead of looking at how much field flows through a surface, and so how much it flows parallel to the area vector, we look at how much it flows along a given path. Basically, at each point in the path we assign a length vector, dl, that points in the direction we're going, and then we compare that to the flow of the magnetic field. So for example, if I have a wire of current here, you can imagine it would have a lot of circulation along this circle here. Knowing the circulation allows us to use something called Ampere's law. The circulation on any closed path around a loop is proportional to the current running through that path. To see why it's useful, let's look at an example. If we go in a circle of constant radius around the wire, the magnetic field will be constant. So just like Gauss's law, we can pull out the magnetic field, and now the integral of dl is just the length of the wire, or the circumference, 2 pi r. Divide those sides by 2 pi r, and you get the magnetic field around a wire. Notice that instead of an inverse square law, like we're used to seeing, the magnetic field decreases only inversely with radius. Thinking back to the Biot-Savart law, this is ultimately because we have a radius vector in the numerator, magnitude-wise, so to cancel with the r squared in the denominator, giving us effectively a magnetic field inversely proportional to the radius. So the magnetic field still drops off pretty quickly, as you can see by looking at the graph of the strength. Alright, now it's time to talk about how basically all major electricity sources generate that energy. Are you ready for the secret? Take a piece of wire and wrap it up into a big coil, and then take a magnet and move it around inside the coil. That's it. If you can find some way to move the magnet or the coil, you got electricity. The mechanism behind this is called Faraday's law. The voltage imposed on a loop of wire is equal to the negative of the change in flux over change in time. So if you increase the magnetic field, you get a voltage in the negative direction. If we want to, we can break this equation up into its raw form. We'll write out the magnetic flux completely, as well as the voltage. In this case, it's conventional not to use the negative sign on the voltage so that the directions work out. Notice that the magnetic flux is not going to be zero since we're not going through a closed surface, we're looking at the flux through a loop. Also, if you remember from earlier, we got this voltage equation from the force from the electric field, Q times E, but we have a new force too, QV cross B, so we have to add that in to the equation. Now this equation isn't really that easy to work with, so we're usually going to stick with the original one. Anytime I change the magnetic flux in my current loop, I get voltage. So looking at the flux integral, there are three main ways I could do this. I could make the magnetic field weaker or stronger, I could make the area bigger or smaller, or I can make the loop in the magnetic field point more or less parallel. Another thing to take note of is the negative sign. The direction that the voltage takes will oppose the change in flux. So if I have an increasing flux in this direction, then the voltage will point in the direction that would create an opposing magnetic field. This is called Lenz's law. You can also use the right-hand rule to figure out which direction the current's going to point in. First, determine the direction the magnetic flux is changing in. So for example, if you start with a strong magnetic field upwards, but it weakens, then your change vector is downwards. Now, point it in the opposite direction, since the current opposes the change in flux. You point your thumb in that direction, then your fingers curl in the direction of the current. One consequence of this is something called eddy currents. If you have a magnetic field, such as this one pointing into the screen, when you move a metal object into the magnetic field, the field through the metal gets stronger, pointing into the screen. To oppose this, the voltage is created in the direction out of the screen, counterclockwise. Now there's also current in that direction, most of which is pointing upwards as the object enters the magnetic field. Using our original right-hand rule, we have upward current and a magnetic field into the page. This creates a force pointing to the left on our piece of metal, which opposes the motion into the plate. Now when the metal moves out of the plate, the magnetic field gets weaker, so the change vector points out of the screen. To oppose this, voltage points into the screen, or clockwise, which also creates upward current and a leftward force on the left side of the metal, opposing the motion out of the magnetic field.
Alright, so now we're going to talk about Tesla coils. Yay! Woohoo!
So the way Tesla coils work is they use something called a transformer. Let's say we have two coils stacked on top of each other like this. In the top coil, we turn on some current, which creates a magnetic field, right? In the second coil, as the magnetic field turns on, the magnetic flux is changing, which means that we get voltage in the second coil. Now the magnetic field in both coils is the same, which means that the flux through each single loop should also be the same, and the change in flux over change in time should also be the same. Now the flux for the entire coil is equal to the flux for a single loop times the number of loops. So the voltage on the first one is equal to the number of loops in the first one times the change in flux over change in time, and the voltage in the second one looks the same. We can solve for the change in flux over change in time in both cases, and we know that they're equal to each other. So we can set them equal to each other, and solving this gives us that the voltage in the second coil is the same as the voltage in the first coil times the ratio of the number of turns. So if we have more turns in our output coil, then we have more voltage. A Tesla coil works by essentially combining two transformers together, giving us a very large voltage. Power is still conserved though, so while we have a really big voltage, our current is pretty low.
Now so far we've been talking about induced magnetism, which comes from running a current. But there's also permanent magnetism and other types of magnetism, which create magnetic fields without running current.
The things we generally refer to as magnets are called ferromagnetic. In general, they'll have different chunks that have magnetic fields pointing in certain directions, called domains. If you add an external magnetic field, then you can get these domains to align, giving you a permanent magnet. Examples of this material are iron and cobalt. The next type of magnetism is paramagnetism. The magnetic fields are usually randomly aligned on a paramagnetic material, canceling each other out. But if you add an external magnetic field, then the material will align with that, giving you a slight extra magnetic field, but it goes away once you remove the field. Examples of paramagnetic materials include aluminum and oxygen. Lastly, there's diamagnetism, which is present in almost all materials. To understand this, you can think of the electrons moving around an atom in these materials as tiny current loops which create tiny magnetic fields. In diamagnetic atoms, the electrons are paired up so that the magnetic field cancels out normally. But when you bring a magnet close to them, you get induction from Faraday's law. So the current running in the direction opposing the magnetic field, that electron that's spinning against it, gets slightly stronger. And so the material creates a magnetic field slightly opposing the magnetic field. Examples of diamagnetic materials include water and most organic materials. And if you can get a strong enough magnetic field, you can make things levitate. For example, we've been able to make a frog levitate with a strong magnet. Just like one of these coils of a transformer creates flux through the other coil, it also creates flux through itself. Specifically, the flux is proportional to the current that we send through the coil, and the voltage is proportional to the change in current over change in time. This is actually the secret third circuit component that we didn't talk about earlier, the inductor. Since it opposes changes in voltage, One way to think of it is to imagine one of those super big and heavy wheels on like a bank vault or something. So when I start pushing it clockwise, it takes a minute to get going. But once I get it going, it'll keep going, even if I start pushing it the other way. Looking at the sine waves, it's going to lag behind the other voltages in the circuit since it opposes changes in voltage. So we can shift it to the right because, remember, further to the right means further into the future. Now if we start looking at this peak right here, we can see that the voltage is at its maximum. At this point, enough voltage has been applied to get the current running through the inductor, and it'll keep running more and more as we push it more until we start pushing it in the other direction. And then the voltage in the inductor will start to slow down more and more again until we're at the peak voltage on the other side. At this point, current starts flowing in the opposite direction, and it continues to do so until we push it the other way. The equivalent to resistance for an AC inductor is its reactance, which is equal to the frequency times the inductance. In other words, a better inductor is going to oppose the voltage better. And also, if the voltage is oscillating more frequently, then it's going to oppose more and more because there's not going to be a steady state of the voltage. If we look at the circular diagram, the vector for the inductor is 90 degrees behind the voltage source. If we have a resistor, a capacitor, and an inductor in series, we can add them up and get the total impedance like this. It's the same thing as before, except now we have to subtract the reactance from the inductor, since it points in the opposite direction of the capacitor. Now since the capacitor is capable of resisting the voltage of an AC circuit, we would expect it to have some kind of energy, and indeed it does. We can get it from a Kirchhoff loop, just like we did before. The voltage from the source minus the resistor voltage minus the inductor voltage must equal 0. Now since all of these quantities are voltage, if you multiply the whole thing by current, then each quantity becomes power, because power equals current times voltage. Now we can get the energy by adding up the power from the inductor, or the change in energy over change in time, along some interval of time. Doing this gives us 1/2 Li squared. One last thing about the inductor is that when you first turn it on, it's going to oppose the voltage source, right? If we're talking about a DC circuit. But after some time, it's not going to oppose anything because the voltage isn't changing. So we can think of the inductor as starting out like an open switch, basically opposing all of the current running through it. Then over time, it's going to act more and more like a wire, letting all the current run through that it wants to. In the next video, we're going to look at how you can combine electric and magnetic fields to create electromagnetic waves. I'll see you there.